Now we will see one problem regularly faced in RCC design. Here the cross section of the beam is given. It is 300 by 600 mm and it is subjected to a moment of 250 kN/meter. It is fractured moment. You need not have to multiply the moment by 1.5, which is the load factor. It is already factored load. And the problem is calculation of area of steel in the tension zone. Here, we have to calculate the reinforcement without the use of SP-16. That is the objective of the problem. How to calculate the area of reinforcement for an RCC beam which is singly reinforced without the use of SP-16. The concrete grade is given as M25 and Fe 500 reinforcement is used. You can see here the cross section is 300 mm. The total depth is 600 mm and the cover of the reinforcement is 38 mm because we are assuming some diameter of the reinforcement. It is in the range of some 25 mm or 30 mm. Normally we will, so 25 mm is the minimum clear cover, and beyond that if you add another 14 mm, which is D by 2, then the effective cover comes to nearly 38 mm. Therefore, the effective depth comes to 562 mm. 600 mm is the overall depth, and 38 millimeter is the effective cover, and 562 mm is the effective depth. Now, the problem of calculation of reinforcement in the tension zone involves assuming some value for the neutral axis. This is based on some trial and error. Now, here the effective depth is 562. Now, let us assume to begin with the trial for the neutral axis as 200 mm. 200 mm is the depth of the neutral axis. This is based on trial. If 200 mm is the depth of the neutral axis, then we have to draw the strain diagram and calculate the strain in the tension reinforcement. Strain in the concrete extreme fiber is 0.0035. This is always constant. Please note, limit state of collapse corresponds to the strain value EC is equal to 0.0035. This is always constant. This distance 200 mm is known. Out of 562 mm, this 200 mm is gone, then this is 362 mm. Therefore, by proportion of this 200 versus 362, based on the value of 0.0035, we can get the value of EST, that is strain in tension reinforcement, that is equal to 0.0063. So, the neutral axis, whatever we have assumed, XU is equal to 200, is within the limit. It should not happen that we are assuming the neutral axis on the higher side. There is a permissible limit. What is the permissible limit for the neutral axis? If the strain in reinforcement is less than 0.0047, then the neutral axis is assumed on the higher side. This value should be at least equal to or higher than the strain minimum value specified. That is 0.87 Fy divided by Young's modulus plus 0.002. That value comes to 0.0042. So this strain is equal to 0.0063. This is very much higher than the minimum value specified for the strain in the reinforcement, 0.0042. This is nothing but it is equal to 0.87 Fy divided by Young's modulus plus 0.002. So we have not exceeded the limit while assuming the depth of the neutral axis. We are very much within the limit because this strain value is higher than the minimum specified strain for the reinforcement. And if this is on the higher side, the strain value will be less than 0.0042 and it is not allowed. You cannot assume beyond certain limit. And the other option is you can always check whether this 200 mm is exceeding the value of the depth of the balanced section. that is equal to 0.46 times effective depth. 562 into 0.46, that will higher than this value of 200 mm. Therefore, we have not exceeded the limit specified for the neutral axis. We are within the maximum limit specified, because this 200 mm is very much less than 0.46 times 562. What is 0.46 times 562? That is the depth of balanced depth of the section. So the value of balanced depth is 0.46 D. That is 0.46 into 562. And this 200 mm is less than 0.46 into 562. Therefore, we are well within the limit. So that check has been performed. The strain diagram needs to be drawn just for the sake of making the work from the first principle. If you are remembering the value of depth of balanced section, straight away you can check whether 200 mm is less than 0.46 D. If 200 mm is less than 0.46 D, then you can conclude that you have assumed the neutral axis very much below the maximum specified value, very much below the permissible value, and you can proceed with the calculation. Now, what is the esteemed fiber stress? It is 0.45 FCK, and this depth of the this compression value comes to 0.36 times FCK into B into XU, 0.36. This is rectangular cum parabolic. Therefore, the average value will be equal to some 0.36 times FCK, 0.36 FCK into B into XU. For getting the value in kilonewton, divide this by 1 power 10 power 3. It is 540 kilonewton. And what is the value of tension stress in the tension reinforcement? That is equal to 0.87 times Fy, or Fy divided by 1.15. That is equal to 435 Newton per millimeter square. Once this value is higher than 0.0042, then the tension, the stress in the tension reinforcement is equal to 0.87 Fy, or Fy divided by 1.15. That is equal to 435 Newton per millimeter square. And the compression, whatever we have calculated, that is 0.36 FCK into BXU. It is acting at a distance of 84 mm from the top. That is, XU is equal to 200 mm, and 0.45 times of XU is equal to that is 0.42 times XU is equal to 80. 200 into 0.42, that is coming to 84 mm. This is the distance of resultant compressive force. And total effective depth is 562. The resultant compression is acting at a distance of 84 mm. Therefore, 562 minus 84 is equal to 478. How did we get this 84? 84 is nothing but 0.42 times XU. XU is this depth, 200 mm. Multiply this by 0.42. Then you will get this distance, 84 mm. Total effective depth is equal to 562. Out of 562, you subtract this 84. Then you will get this 478 mm. Now, we will check whether our assumption of XU is equal to 200 mm is correct or wrong. The external moment is equal to 250 kilonewton meter. That is a given. Now we will take the moment about the tension reinforcement. What is the moment created by the internal compressive force? That is equal to C into this 478 mm. C is the total compression. 478 mm is the distance of the resultant compression measured from the tension reinforcement. Therefore, C into 478 mm is the movement generated internally. Let us check whether they are both of them are equal or not. For the trial to be exact, sigma m should be equal to 0. That is, anti-clockwise movement should be equal to clockwise movement. So the compression generated, the moment generated by external moment is acting in the clockwise direction. You can see here. External moment is acting in the clockwise direction. Internal moment is in the anti-clockwise direction. So clockwise moment is 250 kilonewton. Anti-clockwise moment is C into 478 mm. C is 540 kilonewton. 478 mm, you convert it into meter, 0.478. That is coming to 258 kilonewton. Now, both of them are more or less equal. This is 250 kilonewton meter. This is 258 kilonewton meter. Both of them are more or less equal. So we will provide the reinforcement corresponding to this 258 kilonewton meter. Now C is known and sigma h is equal to 0. Therefore, this tension must be equal to this compression. So tension is equal to compression is equal to 540 kilonewton. And allowable stress for the tension reinforcement is 435 Newton per millimeter square. It is 500 into 0.87 or 500 divided by 1.15. That is partial safety factor, 435 Newton square. So T value is known. AST is equal to T divided by this allowable stress, 540 into 10 power 3 divided by 435. That is coming to 1241 millimeter square. So you provide 4 numbers, 20 tar, that is 1256 millimeter square. So this completes the problem. So this is how you can calculate the reinforcement in the tension zone for the RCC beam without using the SP-16 or without remembering any formula. This is the working based on the first principles. Friends, I also request you to visit my blog, https://rgnsite.wordpress.com. Here, about 500 university questions and answers are given. 500 detailed university questions and answers are given, covering various structural engineering subjects, RCC design, steel design, strength of materials, theory of structures, volume 1, volume 2, such as matrix methods of structures, moment distribution method, calculation of deflection, strain energy method, slope deflection method, etc. And also structural engineering subject for DCE board exam. All the structural engineering subjects are addressed in this https://rgnsite.wordpress.com. For about 500 university questions and solved examples, 500 university questions and answers are given. One-word questions and answers are also given apart from these 500 university questions and answers, and the download is free. So please visit my blog, https://rgnsite.wordpress.com. Also visit my channel, RGN Class. Please visit my channel, YouTube channel, RGN Class. In the search engine for the YouTube, type RGN Class. You will get some of my videos along with other videos. You choose one of my videos and there you will see one icon R. You press that icon R, then you will see all the videos of mine without clubbing any other irrelevant videos. Choose one of the use RGN Class in the search engine of the YouTube. Some of my videos will appear along with other videos. Choose one of my videos. There one icon R will appear. You press that icon R, then you will have all my videos under the heading RGN. Thank you for your patient listening.